All right, I think we can start. Welcome everyone to the third EWL workshop and its webinar series. Before we start with webinar number 5, I'd like to do a few acknowledgements. First, I wish to acknowledge the people of the Kulin Nations on whose land we are gathered today, and I pay my respects to their elders past and present. Furthermore, I'd like to acknowledge the generous support and funding from the Australian National Fabrication Facility, ANFF, and its CEO, Jane Fitzpatrick. And of course, big shout out to the DWL Workshop Organizing Committee for their hard work to put the webinar series and the upcoming workshop together. Also today, I'd like to acknowledge our generous sponsors, especially the platinum sponsors, Micromaterials and Nanovacuum, who also supported this webinar series with 2 webinars. And of course, our sister meetings, conferences and workshops, Mabel, 3Beams meeting, and the Thermal Probe workshop. All 3 of them are registrations open. I also like to mention that as the last 3 years, we are doing a Mabel Asia Pacific meeting hosted from Australia on the 8th of August. So we will re-advertise once we're closer to that date. And this brings me to today's webinar number 5, EBL Resists and their exposure mechanisms from pMMA to hydrogels, presented by Leonidas Ocola from the IBM TJ Watson Research Center. A few words, a quick introduction. Leonidas has his MSc in physics and PhD in physics from the University of Wisconsin in Madison. He was the staff member of several research facilities, most notably the Center for Nanoscale Materials in the Argonne National Laboratory. Since 2017, he's a member of IBM TJ Watson Research Center. He's also a member of the American Physical Society and the American Vacuum Society. He chaired EIPBN in 2013, and his research areas, Dr. Ocola's research interests include electron beam lithography, and that's what we're going to hear about today, simulating high-energy electron beam interactions with polymer materials, scanning probe characterization techniques, FTIR, microspectroscopy, single-molecule spectroscopy, nanofabrication, metal oxide devices, ALD infiltration in nanostructured polymers, and the properties of such modified materials. Leonidas, we're looking forward to your presentation. The stage is yours. Please go ahead.
Thank you, Michael, for the opportunity to share my work with you guys. So let me get my screen shared. Okay, can you see my screen?
Yes, and your pointer as well.
Okay. Yes, thank you. So yeah, I'm gonna be talking about and trying to set up the foundation for understanding how e-beam resists are exposed, and then we'll go through some case examples with pMMA and hydrogels. So that's the focus of the talk. See here. All right. I'll always like to start with this little tidbit of history. It's good to look back. And in this particular case, the Native Americans of southwestern USA were the first ones to actually have a lithography process, in the sense of you have a resin, you draw your pattern, you then put that into an etchant, do wet etch, and remove the pattern, and you have your engraved shells. And this was done hundreds of years before the first decorated armor using engraving or this type of process was done in Europe. So that's pretty cool. So lithography is an old technique. In terms of electron matter interactions, we've been studying electrons and how they interact with materials for hundreds, almost a couple, see, was it 130, 120 years? So there's a lot of work and a lot of communities that have been studying these interactions from different perspectives. And sometimes it's good to look outside of the box of lithography to get some type of insights that may have been developed elsewhere. So the first direct write that I found was this in 1926. It was not and it actually had a focus element, and low voltage electrons were used to trace into photographic film. And yeah, you can actually find this paper, 1926. So it's very interesting. And the key, this was the original resistor materials that people started working with in how electrons were interacting with matter with these photographic emulsions. And we'll see how that works out as we go on. The first E-beam resists were actually from Kodak, which is these photographic emulsions. And they were called KPR for Kodak photoresist, which is very original, and so on. But these were the known resists at the time, and that's in '65. And they were already looking at how these resists worked and interacted with electron beams. 68 was when pMMA was first introduced by IBM. Now, pMMA as plexiglass is been known before being a resist. So it was just the work of Mike Hatsakis and company that really proved that you could use a spun-coated pMMA as a high-resolution positive resist. And to date is one of the most highest resolution positive resists as it is. So there are better now, but it's still pretty up there. And it's heavily used in the E-beam community, probably the most popular resist in the E-beam community. Maybe HSQ is second place. And after that, then started the look at resists that were positive and negative, and also sensitive to optical lithography and E-beam lithography. These resists up here, the emulsions were all negative. So here is where now we start to try to look at, okay, so these films have certain interactions with light and certain interactions with electrons. And that becomes part of the theme of trying to understand the mechanisms of the exposure mechanisms and resists for E-beam. And the at pMMA, MMA, I'm sorry, what was that? Okay. pMMA, MMA polymers were introduced then 10 years later by Mike Hatsakis. And let's see, is there something I need to see in the chat? A second. Oh, okay, never mind. And he's basically if you want to call it the godfather of liftoff, because he introduced this concept of using these two polymers that had different dissolution rates to be able to do liftoff. And his paper showed some of the early structures used for devices using liftoff. Okay, so yes. So as I said, there are plenty, and then mix and match right now is pretty important. Try to find resists that actually are sensitive to both optical lithography and E-beam lithography. There are different types of optical lithography. There's the mid UV, which is 365 nanometers, which is about 3.4 EV. DUV, 48, 5 EV. I always like to use the energy part. 193, which is 6 EV, and then EUV, which is 95. Now, it's good to look at these because when you find out what's the binding energies, if you want to look where are these doing any ionization at all, and the answer is no, because the lowest binding energy for hydrogen, carbon, and oxygen are above 13 EV. So if a resist, it's interesting. Here's where we don't know when electrons are interacting with these resists, and this is the energy that they're activated to respond to. Is it really ionization, or is there something else going on? So this is where we're going to go into more detail. And now EUV, yeah, it is an ionizing radiation, but it won't be able to ionize any of the core electrons from oxygen or carbon, because those are in the 200 plus EV binding energy. So you're probably not going to get any Auger from an EUV exposure. If anything, it might be from an outer shell, but really, I don't think you'll see anything. Now, not all, obviously, not all resists that are in optical are sensitive to E-beam. And I just experienced this past year with a colleague of mine. We were trying to do more mix and match and look at this one of these MUV resists. This is an MUV resist. And no matter what we did, we blasted up to from 10 microcoulomb to 4,000 microcoulomb. So, about 3 orders of magnitude. And nothing. We didn't get to develop at all. So it could be that maybe we're just cross-linking, but this was a positive resist and we weren't getting any positive resist response. So also the Shipley 1800 are notoriously finicky. Very, very, very small process window where you might get an opening, again, positive resist, but really not worth trying to do the effort. So yes, so this is where I bring up, yeah, it's important to understand that how these electrons interact with resist at a more fundamental level. All right. So yes, you've seen some of this stuff already with Scott Lewis's talk and his nice detailed talk. I'm going to go a little bit over some of these things, and but in reality, the first half is going to be on this part, and the second half is applications. I don't want to spend too much on this modeling part, but I think it's important. So elastic, you got elastic interactions, you got inelastic interactions. And you can model the elastic using something called Mott cross sections. I know that Scott used Rutherford. In the inelastic, you have obviously the ionization, but then you have possibly plasmons, because you definitely have a sea of electrons that will respond collectively to an incoming electron. But then you have other things, molecular excitations, temporary negative ions. This is where it's almost like an electron trapping, but after it's done doing its stuff, it spits out the electron again. So it's not really a trap, but it is definitely some type of temporary trapping. And to explain or to describe these, there's different type of models. And what Scott explained earlier was this continuously slowing down approximation, but there are many others. Binary encounters, what I've used in my work. There's also something called a virtual photon, which is pretty cool idea, which tries to bridge this concept between an optical excitation and an electron excitation. And then there's also some more other things called dielectric function and so on. And yes, the continuously slowing down approximation uses something called a stopping power, which is basically the integral of all possible inelastic losses at a particular energy. It's a single number. You lose some of the details and information that could make useful trying to model a resist. Yeah, so I already talked about this, ionization. The boundary encounter model, that is good for ionization. And all you need is the periodic table, in the sense of all you need is, okay, what atoms are there? What are your levels? What is the binding energy per each level? What's the occupancy, or how many electrons in each level? And it uses a semi-classic approach. And in reality, it can be tailored to be as detailed as you want. And so I find it very, very flexible and useful. And I'll show in a bit. Yeah, so the earliest person who started this was Grzyński. So if anybody's heard Grzyński cross sections or heard me say people, oh yeah, I use Grzyński cross sections because of this. But other people have improved on it, and actually I should have taken myself out, but yeah, as part of my thesis, I modified some of the work that Kim and Rudd did later on. And yeah, this virtual photon is pretty interesting, where you have you try to explain the energy transfer as a virtual photon transfer. So I want to convey that this area of research is not closed. It's still, I think, pretty open, and there's I think a lot of exciting stuff that can be done. So this is the concept of this virtual photon, and there's the paper. I'm not expert at all in this, but I thought just to bring this up as a, hey, you know what? Maybe this is another way of looking at electron scattering. We know that the electrons has a linear electric field, okay? So as it's traveling, the electrical field is propagating in that same direction. Meanwhile, a photon, the electrical field is transversal to the direction of the photon travel. And so how can you represent this? Well, it turns out that there's a time dependence. As the electron gets, suppose that there's the atom here in S, position S, and you're traveling at a distance V with a certain momentum and energy. So the electrical field is going to at one point be pointing down, then it's going to point horizontal and point upwards. And so if you integrate that, you actually have a net transversal electrical field. And so you can decouple that into, or these type of photons, perpendicular and horizontal, and then you can more or less describe, oh yeah, so now we're going to couple into some optical resonances which people have measured, right? Optical spectroscopy is well established. So if you can associate then what frequencies you're working with that particular resonance, then you can maybe describe better how the interactions happen. So as I said, right, here's the cartoon. So this is the magnitude of the field as time goes by. So you can see it ends up being intense perpendicular, and this is for 1 kV electron. So that's a pretty interesting thing to look at. I did not so when this work came out, I was already gone at Bell Labs, but I did not really get into this. But I think that I thought it was interesting to bring it up here for you guys. Maybe somebody be look into that. So now, yeah, this is so our colleague, Scott, he described inelastic using the Beth cross sections or stopping power and the Rutherford elastic. Well, those were, the Rutherford cross sections were established in 1911, and Hans Bethe did his work in 1930. But obviously, a lot of people did work afterwards, and so Gruszinski was 65, Rudd was 94. I was actually a grad student at the time, and so I found this really, really interesting. And so I'm using Massey cross sections, which has been in reviews. If you go to the NIST website, you can actually download all these cross sections. But they've been compared and they've been demonstrated they're more accurate than any of the other elastic cross sections published. And then from an inelastic point of view, there are others. This is the one that I used. The Gruszinski based, it's truly stochastic. It only relies, I said, on binding energies. You can see how many electrons are in each level. Atomic density. So you need to know, right, how many atoms per unit volume are in your resist. And then you can do you use that as your weight for the cross sections. And because of that, it's easy to implement on any arbitrary material. But obviously things get more complicated, and so we'll see all that. So this is just a first view of what does an elastic cross section look like. And so this is I was fortunate enough to find somebody who could calculate, had a program. So when I was around, Fortran was pretty popular. Probably some people don't even know what that is, but that was pretty popular, and it was an ASCII-based programming, and I just had to compile, and voila. So it was easy to understand. This C++ and other things, it's a little bit too much for me. But the bottom line is here, I could calculate, these are data points from my calculation. So I covered from 1 EV all the way up to 100 kV with about, I think, 25 data points. But you can see that, yeah, it's pretty smooth. But this is how cross-section for carbon, which is what you would find in the resist. And this is the cross-section for silver that you wouldn't find in resist, but it's just to show the difference between a high Z element and a low Z element. And there's two overlap because these are at the same scale. It shows you that at the really low energies, the carbon is going to scatter more than the silver, but at the higher energies, it's the silver that's going to scatter more elastically than carbon. And so basically it's telling you, okay, well, it's going to go further straight down in the resist than if it was hitting a film of silver. These are the differential elastic cross section. So this is basically the cross section for each angle. So here I go from 0 to 180, and these are for different energies. So I picked 1, 10, 100, etc. These oscillations here are just floating point errors because we're talking, we have to deal with double and maybe even quadruple precision in order to get the numbers right. So I'm not too concerned about that. And if any case, this is maybe where, your Rutherford may be better because it's just a simple formula. But Rutherford would never be able to predict this dip here. And in silver, you can see you got even more complicated dips. And so all what it's telling you is that, for example, let's go back to the carbon. All right, so about 105 degrees is the least likely angle, scattering angle for carbon. You're going to have mainly dominating, this is at 10 eV, dominated just forward scattering, but there's also a good amount of backscattering, so at 180. And so this will affect the distribution, the spatial distribution, where the energy is going to be deposited. Because this is the elastic scattering is really what's telling you what trajectory things are going. And this is where we talk about momentum transfer. The large momentum transfer is going to change the direction of your electron. That doesn't necessarily mean large energy transfer. It's just there's things that we have to distinguish when we try to model or understand what's going on in the resist. And this is an example of a paper from Kim and Rudd in '94. I mean, I got my PhD in '96, so I was just about to finish, and I saw this, and like, oh, I need to change gears. And I found this really exciting because what you're seeing here is a benchmark, and I'm going to emphasize it's very important when you do work to benchmark against known results. And so they benchmarked their cross-section, which is the solid line, to actual experimental data. And this is for water vapor. So it's a multi-element material, right? So again, imagine now a resist like pMMA. It's got three elements: carbon, oxygen, and hydrogen. And you can see that it fits very well in the low and the high energy, and pretty decently in the mid energy at 100 eV. So this is why I picked this particular model, the binary encounter model, as the basis for trying to understand how things work, and you'll see what type of information you can extract once you implement this model. So now we're considering non-relativistic electrons, so 100 keV and below, because you start going to the 250 and above, now you gotta do relativistic, and it's not really, there are not many tools that do that. We're also considering single scattering events, so no multiple scattering. We're just going to do one at a time. And we separate the sea of electrons from the atomic nuclei, so that in atomic nuclei is where you got the elastic scattering, or it is bouncing off, or significant momentum transfer. They're basically synonymous. And there's minimum energy transfer, right? Because it's elastic. And then you got the sea electrons, which respond very quickly to the incoming electrical field. And so therefore there is minimal momentum transfer because they're not putting any resistance for the other instant electron to bounce off of, but there's going to be significant energy transfer. And so, as I said, we have to not only look at ionization, there's other excitations at the really low energies that need to be considered. And so we do this, and when you do modeling, you have to include both things happening at the same time. All right. So yeah, so the idea now is, okay, we're gonna use the concept of, yes, cross sections. And I'm not gonna, so unlike David Joy's approach and what Scott showed, where you're gonna use the mean free path and try to use it. No, I'm gonna go basic cross sections. The mean free path is gonna be an output of these cross sections, because that's going to be basically, it's the most likely or the mean average path of interaction where something happens. So that should come out of the Monte Carlo using cross sections. It's not an input, it's an actual output. And so, you're going to have to deal with these two. Then you have to go, if there is an inelastic event, which inelastic event, and then which excitation, and you go down the tree of, okay, is it what type of ionization, what atom, what atomic level, which electron, or what energy is being transferred, how much momentum is being transferred. All of that stuff gets calculated once you trigger the inelastic event. And so there will be, what we're going to define is the probability function of an interaction or travel distance inside the medium. So we're going to actually follow each electron as they travel along their path. And in this case, I think I'm using 2 angstroms path steps, which seems really small and it seems like, oh, it's going to take forever. And actually, no, I get really practical results, and I'll show them this talk. And the other thing is, I use this, it's called a Monte Carlo inversion method, which I'll explain pretty quickly in basic mode, what it means. But that is what I do. So I have, let me see if I have, and that's where that random number will be come into play. So don't get scared. This is a big formula, but in reality, it's just a bunch of constants. And this fancy E is the incident energy of the electron, and this fancy U is the binding energy. And if you look, that's all what it is. And there's a term called direct, there's a term called exchange, and there's a term called interference. And that has to do with distinguishability between the incident electron and the electron that's being ionized. And I'll get into in more detail these explanations in a bit. But so you basically, the total ionization cross-section is going to be the integral of all the partial for each atomic level, right? So we have to integrate all the possible energy transfers, differential cross-section for every single atomic level, right? And so 1 second here. Yeah, this is the actual differential cross-section. So this sigma delta E is this other formula, but it also has a direct exchange and interference term. And again, it looks scary, but in reality, it's just a bunch of energy transfer, and binding energy. Those are the terms. The rest are constants. That can be modified a little bit depending on if it's, for example, a transition atom, or there are some corrections for really high energy or really low energy. But at the end, it's just that. So in reality, all you need in order to find out this differential cross-section for a particular energy transfer is the periodic table. That's it. It's pretty easy, quote unquote. Obviously, took me a while to understand this. Here's the actual description of the terms. I wanted to wait until I get this over here so I don't mess up. So the direct term is where an incoming interacts with a target, transferring momentum energy without exchange of identity, and that's the key. Okay, so you can actually tell who's who. And then, for example, if I have that 100 kV electron coming in and it knocks off a carbon 1s, the 1s is going to come out, let's say, well, you're going to lose at least 280 eV from the incident. So that electron that came down is going to be 100,000 minus 200. But the other guy that's coming out will probably come out at maybe 1 eV, because you have to transfer the binding energy, and whatever's left over is the kinetic energy. And so you can tell that they're very, very different electrons. The key is, if in some case, if there's, let's suppose, a 40 eV electron coming in, and it knocks off something that is at let's say 10 eV, and it gives kinetic energy enough so that you both have the same kinetic energy. Now they're not distinguishable, and so you have to have this exchange term, okay? Because you don't know who's who. And then there's the interference term, which then comes between, the mathematical term between the direct and the exchange amplitude. So if these two interfere, you got another term, okay? So this approach that I'm talking about, these formulas here, is almost quantum mechanical, but it has a semi-classical startup where you set things up. So it is really going into more detail of how the electrons scatter in the material. I found that fascinating. That's why I picked this one, because just trying to go with the stopping power, stuff that was boring, that was done in the early 1900s, I thought that was not worth really working on. So looking at this, I thought it was pretty cool. And then you got the momentum transfer, and I'm not expert at all in Feynman diagrams, but this is the only one I could understand, where you have an incident electron, it transfers certain momentum. Here's the other electron that has its own momentum, and so you get a vector diagram. And so because of conservation of energy, you have a specific constraints on how much momentum is being transferred. And so you can calculate then based on this, based on the energies, you can actually then calculate the angle, the scattering angles. And so you don't have to worry about other formulas, it's all built in. And so you have to also consider the momentum transfer in your stuff. And the binary encounter model has this already in there. If anybody's interested, just you saw the papers from Verns and Kim and so on. They're very, very enlightening on how they explain all this stuff. Again, this is 30 years ago, that 96, and we're 2025. So this has been a long time. There's a lot of stuff I've forgotten, but this is, I think, pretty cool in how it explains. You can, from basic physics, you can get your scattering angles for inelastic events. And so now we go to the probability, and so this is like your Beer-Lambert law. This is the differential cross-section of an event that happens as something is traveling a distance s inside a material. And so in our case, we have different events. We have elastic events, ionization events, and plasma events. And we can add these probabilities, or these differential probabilities, because these things are independent of each other. If I have an elastic event, I definitely don't have an inelastic event. These two guys are inelastic events. And if I have an ionization event, which is, I can't have a plasma, which is a non-ionizing event. So again, these two are exclusive of each other. So I can add these probabilities. And so then each possible probability is then going to be based on the number density of the element that we're going to consider the probability, the cross section, in this case, elastic or inelastic or plasma or non-ionizing, and this form here, and times the travel distance. And so these are the things that get added up. I'm bringing up this paper in 2013. I collaborated with Professor Brainerd at CNSE, or what used to be CNSE in Albany, and his students worked with me, and they modified my code to C++. So now I don't understand it, but it works, and they've used it. And so if you guys want to contact them, feel free. But there's they've basically modernized my stuff, and they've actually included some really low energy interactions to actually improve what I started. So it's pretty cool to see what it can do now. So I mentioned the Monte Carlo inversion method. So let's assume you have a probability function here. Okay, so there's a probability that x at certain position it will be existing, and it's 0 at any other x, this p. And so the integral of that is this. And so all you do is now you have, this is your 0 to 1. It may never get to 1 in this particular case, but your random number can be 0 to 1, and you're throwing darts. And if it hits the board, then you can go down and calculate which X did that probability correspond to. So you can actually recreate, based from the CDF and your random number generator, you can recreate this function here. And so here's a slight cartoon animation. So let's suppose that I have a particular random number at this point. And so all I do is, since I know all my cross sections and the formula is a function of energy and stuff, I just run the integral of these cross sections until I hit the jackpot right here, and then I can do interpolation and calculate that particular angle, or that particular energy transfer, or that particular momentum transfer, and so on. So that's how this inversion method works. So it's all based on cross sections, and I can add as many cross sections as I want, as long as they're independent of each other. Or if they're dependent of each other, I can make it a little bit more complicated. But the bottom line is that you can really go through that way in a fundamental way to get the interactions. So obviously, as I said, you want to benchmark. So I found at the time, I was working in X-ray lithography, and people want to know the resolution of X-ray lithography. And so the leading guy in modeling X-ray lithography and photoelectrons was Kenji Murata san. And so, yeah, my model matched his very closely. So that was telling me that I was at least on the right direction. The other thing was, well, as I said, the stopping power is the integral of all possible energy losses at a particular energy. Well, I have all the cross sections, so I can actually do the integrals and see if I can replicate the stopping power. And I did. So this is for 4 different materials. I mean, we got silver, pMMA, gallium arsenide, and gold. And I believe, let's see here. Yeah. So the lines is my model, and the symbols are the data points off the literature. So I was doing a pretty good job. And so this is just a proof to show that, yeah, you can start off with these particular cross sections in the way that I described them, and you can calculate the stopping power for any material. You can calculate the mean free path, things that were stuff that was the basis for other people's models. I can calculate it from first principles, basically. And so now we have that. Now we can apply this to real stuff. And so here's where the fun things will start. And so this is just something that just to explain what you can do. So you got multiple materials. You got silicon dioxide, a DUV resist. This is for 100 kV, and we're just showing, where the inelastic events happen and how the electrons fan out. They fan out more in a material that has higher density than resist. So resists have typically densities of about 1.1, 1.15 type of thing. Silicon dioxide is of the order of 2. Silicon is, I think, is 2.3 or 3, something like that. So yeah, and so it's interesting how it goes through these materials. Again, this is what we have, and yeah, this is my very first paper, I think. This one right here, 93, using this model. And so here's where the power of being able to know what you're using the atomic levels starts to come into play. For example, in this particular case, I wanted to know, given a resist, what is the distribution of kinetic energies of the secondary electrons? Because you want to know, right, how far do they travel, and what's the impact and stuff. And so this is basically the peak is at around 10 eV. And this is the integral, and it's just to explain that, okay, 90% of the secondaries have kinetic energies below 100 eV. So so these are typical things, and so most of your energy loss events are below 100 eV. And so we're pretty much using, if we go back to that direct model and stuff like that, the direct and indirect and stuff like that. So at least at the beginning, the incident electrons have E-beam. Most of those are going to be just direct interactions. There's no exchange because that second electron is coming out at such a low energy. You can really distinguish the two. All right, but it's when you get really low energies. If I have an electron like an EUV, the generate electron, now we're in this regime, and you may have exchange terms. But this is and then you can also say, all right, which element is the most dominant one that's generating secondary electrons, right? We know the composition of the resist, and so in this case, it's carbon. You got the hydrogen, right? You got carbon, oxygen, and this is we had some photoacid in this particular resist, so you can see even though the Z is large, you know, sulfonium and iodonium and all these fun stuff, which have really heavy Z's, but because the loading of the photoacid is only 5% of the original loading of the material, so this is where that weighting of how many atoms per unit volume come into play. You can see that really they almost insignificant role in the secondary electron generation. It's pretty much dominated by the stuff that's carbon and oxygen and hydrogen, particular carbon. And then which atomic level? Now you can tell. Okay. So as I said, you know, your 1s, even though it's got, you know, it's right next to the nucleus, and you think it has a higher cross section, which it may, but in reality, it's the outer electrons, the 3s's that dominate in terms of producing secondary electrons. Then come the 2p's, and it's interesting that the 2s in carbon has more electrons coming out than the 2p, but for oxygen it's the other way around. So this is where now you start. Okay, if I really want to like tailor a particular resist, or you want to understand, like, oh yeah, this is where I'm getting my secondaries, and yeah, it's a function of energy. You know, 100 kV, it goes straight down through half a micron resist. These, you know, there's for a time a lot of people saying, oh, low energy electron lithography, there's no backscattered, high resolution. Well, it really fans out very quickly when you're in the 2 kV regime. 25, okay, maybe if you're at about 50 or 100 nanometers, you can do some high density stuff, but in reality, you got a lot of fanning out. And this is just examples of things that, yeah, I've done. This is pretty amazing. This is at the time, this is a 193 resist and at really low dose. I mean, if you consider that 100 kV pMMA is of the order of 1,000, this is 100 times more sensitive than pMMA. But we're not exposing this 50 nanometer line. We're exposing the stuff that's in between. So the resolution is not great, but the thing is that it stops, and you can actually distinguish unexposed or you know, stop the development, so you can actually have a structure like that. All right. So one of the things that I think in the literature for electron scattering has been misused was there's a lot of people that scale parameters as according to Z, to the atomic number. And in reality, that's wrong. It's not correct. We did this experiment with David Sapluski and myself on measuring, we wanted to find an accurate way to measure the backscattered electron range. And we wanted to do it for different materials. And so we actually had substrates. Well, silicon is easy, but we had diamond substrates, gallium arsenide substrates, copper, an actual copper plate, and an actual tungsten, a piece of tungsten. And we exposed, I believe this was HSQ, and we did it's almost like a donut model. If anybody remembers that, it's a way of exposing so that you get what you're measuring is now the actual range. But we found a way to get our errors, our experimental errors, better than 0.5%. And so what you're looking at here in this plot is the basically the intensity or normalized backscatter contribution as a function of radius for different materials. And so tungsten is the highest density and highest Z. Okay, great. Copper has next density and next Z. But then you have gallium arsenide, and gallium and arsenic have a higher Z than copper. And they have a lot less density than copper. And then you got diamond, which has a much lower Z than silicon, but the density of diamond is a lot higher than silicon, which is this red guy. And then silicon is the least dense of all of these guys, and has the longest range. And so the backscatter range is definitely not a function of Z. And I don't think much of it's, it has some weight, I mean, in terms of number of electrons, but if I can pack low Z elements in a higher density than a high Z thing, I'll get more scattering off the low Z even because it has a higher density. I'm just packing more electrons that will interact with the incident electron than just a regular high Z element material. So, and here was the fit of those ranges as a function of density, and it's a simple 1/, density function. Here are the parameters, and the calculations, you see there's calculation 1 and calculation 2. Calculation 2 is actually my Monte Carlo code, and it pretty much lands exactly where it's supposed to be. Calculation 1 actually was just David decided to look at some really mundane, very simple model where I think it just went straight down and then straight back up. And it more or less it follows the density. I mean, as you can see, there's a discrepancy. It's overstating the backscatter range a bit farther than what's supposed to, but still, yet the actual fact that it's following the density is pretty cool. And so yeah, I think this is pretty I can say conclusive that you have to consider the density in a lot of your calculations for electron scattering. Okay, and so my world was X-ray lithography, E-beam lithography, and then I started collaborating with Professor Brainerd and his group for EUV lithography. And so my stuff, yeah, it was okay, but then they ran some experiments, and I was like, oh my God, so this is an experiment that they ran. They were trying to estimate thickness loss, and they had these are chemists, so no offense, but it's just they have a completely different way of thinking, and Robert had some really interesting questions that he was asking from a chemist's point of view that I had never thought about. And so they have really, really cool experiments where they could associate the thickness loss with the electron scattering, and my code was falling flat, and what it was because I was not going low enough in the range. I was going, I think, up to 10 eV, something like that. And so when they went down to the 3 eV, you can see on the right, then it starts to fall. It starts to follow very well the experimental data. And so we started to thinking, like, what are these mechanisms that really go down to the 3 eV? So you got, as I said, you're going to have the electron trapping. You're going to have the transient trapping. You got an internal excitation where it's almost like an optical lithography, because that's what optical lithography does. It's just an internal level-to-level excitation. So that can be done. And then you got some whole initiated chemistry where, okay, it's Kozawa. He's got his own mechanism. So we have to consider all three possibilities. And it seemed like this one was the one. And one thing that you can do, well, if anybody's interested, but what can be done, as I said, there's many communities that have been interacting with how electrons interact with polymers, electrons interact with even just photoacids in specific. There's something called EELS, right? Energy loss spectroscopy. And so there's low energy electron loss spectroscopy. And it turns out Amrit, the first author in this paper, he found a way. If you know the parameters of your experimental setup, because you're measuring energy loss as a function of energy, incident energy at low energies. But if you know, right, the angle, the area, the not only that, but the current coming in and the current coming out, and your detector area, you can actually get the probabilities out of that. You can actually get the cross sections, and since that's a cross section, you can just add it to this Monte Carlo code that I had as another cross section. And it turns out that then we started seeing really interesting stuff. We were actually matching EUV experimentation, and I'll explain that. And this is the key: was from a chemist's point of view, they actually know how many photoacids are generated for an incident photon. They have a way, and so it turns out that it was my stuff was underestimating the yield, but then when modified by Amrit, we got very close to what other people got, 3.5, 3.7 plus and 4.2. Now we're a lot closer. So then this is quantum yield, iodomium. So it's around 5 per photon. And so it turns out that, yeah, ionization on its own is not sufficient. Because it's just the energies don't match. I mean, you need to get really low energies, right? You got an incident 80 eV electron, and somehow you gotta generate 5 photoacids. So it turns out that you have to consider molecular excitations, and they did, and it turns out that we were getting this thing, and so as I said, this can be expanded. It's just people start looking at people already published stuff, is collecting the data and started generating cross sections. So yeah, I think this is a good time for a break, and so the next is now the fun stuff where I'm going to apply this to actual systems, and we're going to look at how pMMA works and how Hydrogel will work, and I hope you're finding this of interest.
You want to continue, Leonidas?
Yeah. Yes,
right.
I would like to. All right, so I hope this goes away. All right, I'm not sure. Is the top part being blocked?
What do you mean by being blocked?
So is there anything in front of the words electron scattering?
I can only see it's not enough just to do electron scattering simulation.
Okay, then we're good. I'll continue. All right, so yeah. So it's, as I said, and this is the title, really. Okay, so we done electron scattering, we see what electrons are, but if you really want to go and understand how resists work, you can't just do a map. You need to look at the chemistry. Okay, what chemistry are you generating? Is it a scission? Is it a crosslink? Are you affecting the molecular weight distribution? Are you generating photoacids? And how does that work? After the chemistry map, you have to convert that chemistry map into a dissolution rate map. And so it's either, pMMA is well known since the 70s how to convert molecular weight distribution into dissolution rate, but then how do you convert that for chemically amplified resists? So this paper is actually one of my best papers on this topic. So you'll see it pretty frequently. And then after that, you want to actually replicate the topography. And so you need to be able to convert that dissolution rate 3D map into a 3D topography. And so I came up with my own ray trace cell removal model, because there are people who only do ray trace and there's people who only do cell removal. But in reality, I find that combining the two is the best way, and I'll show why. All right, so now chemical amplified resists not just the polymer and the photoacid. There's other things. There's plasticizers, stabilizers, there's dissolution inhibitors, there's a base. If it's a negative resist, you're going to have crosslinker. And in the positive resist, the polymer chain will have a protecting group. And obviously, there will be some residue solvent. Solvent can be an actual diffusion channel for photoacids, so that's why it's still there. right? So this is way back when. Turns out that in the DUV resist, here we're trying to compare who's absorbing the energy. So the polymer in an optical, the polymer absorbs about half the energy, a little bit more, and the PAG itself, even though it's only 5% of the material in the resist, is absorbing about half. On the other hand, in an E-beam, 95% of the energy is being absorbed by the polymer. Very little is being absorbed directly by the PAG. So that means that the photoacid is experiencing the shower of secondary electrons generated in the polymer. It is not a direct ionization that's really the main responsible mechanism for exposing a chemical amplified resist with E-beam. And so, yeah, this is just to explain how photoacids work. But what I want to go over is, yeah, so typically you have a polymer, and there's this group. This is the responsible one for interacting with the developer. And so you can knock it off, or you can remove it and protect it, and that's how you get the acid. So the acid moves. That's the H plus will move around, and it will create things. And so you can see this thing disappears. This is that benzene ring, I suppose it's called. And then there's some byproducts. And then the acid keeps on going. So that's how photoacid, that's how chemical amplification works, because the chemistry gets repeated and repeated and repeated. So the number of chemical events gets amplified. That's where that amplification comes into play. All right. And yeah, one of the reasons they wanted to do is because of etch resistance. So here's another thing, but I was able to get information, and then we're going to use this stuff in terms of, okay, find out how many atoms are in each of these elements or moieties, and really we're going to look into how we can model this stuff. So here's just a cartoon to describe the difference between a positive resist and a negative resist. We know that the negative resist, if you don't expose it, it just dissolves, right? So that means it has the maximum amount of soluble sites available. And you call the positive resist, if you put it in the developer, it doesn't at all. So that means that every single possible soluble site has been protected somehow. And so what you do then is, in a positive resist, that photoacid goes around and knocks off the protection locations. So now you have a lot of sites that are soluble. And on the other hand, a negative resist, that cross-linker, which is typically known as pMMA, starts binding to the deep protected sites and making them protected. Now, interestingly enough, and this is work that a colleague of mine did, for chemical amplified resist, typically people think that, oh yeah, we just increased the molecular weight of the polymer, and therefore that's how come it's not dissolving. And actually, that's not true. It turns out that the number of chemical events per crosslinker, which has 6 arms, is 1.5. So that means that the probability is either you have 1 or maybe 2 links, and that's it. And which means that you can't really be relying on this to really bond into too many adjacent polymer chains, because you only have like 1 or 2 max. And so it's not really a molecular weight change, it's really a decrease in number of soluble sites that are available to be dissolved. That's the mechanism for negative chemical amplified resists. And so you can actually, this is just a dissolution rate as a function of density of deep protected sites. And this is for these are 2 resists, and this is experimental data. But just to visualize, as I'm exposing a resist, the density of deep protected sites or available to be solubilized will increase. But for a negative resist, it actually goes the other way. That's, as you increase the dose, it'll go down. And so using this concept, and this is the model that I used, you can actually replicate going from chemistry to dissolution rate, and then eventually to topography. And another thing that was very interesting that I learned when I was writing this paper was that the photoacid in a negative resist, okay, diffuses farther distances than in a positive resist. They don't diffuse the same distance. And the reason is that, and I'm going to go back to this cartoon, these sites are polar. Let me see, go here. So when they have photoacid, so here, these sites are these pendant groups are polar. That means they have some charge, more charge than these other guys. So this can travel. I mean, while this gets like in a satellite type of location, it just gets pulled in and it doesn't travel as far. So you have to consider that. And this. I mean, I checked with literature and experimental data. And so yeah. So when you know that, then you can actually simulate this, and then you can use. So here, this is a random walk, and we're looking at how photoacid travels as a function of time, considering that we're changing the nature of the link, going from a polar to nonpolar, if it's positive, and going from nonpolar to polar if it's a negative. And so, again, in this paper, but it's very interesting to see that we're talking, you know, it could be double the distance at some point if you let it bake long enough. And so now one of the things that you do then is, instead of using, I like to work with probability, so I just used the density of the elements and said, okay, I know my density of elements, and if I have a you know, atomic ratio, atomic weight, I can know what the concentration is. I know the concentration of the PAG. I know how many polymer atoms are per. I can calculate then the number of polymer atoms per cubic nanometer, and so on. Number of pendant units, which are the protected groups, and backbone units of the polymer, and so on. So I can use this to then calculate what's the probability of a photoacid or a polymer chain or a crosslinker that would exist in a particular cell in my simulation space for a resist. And I don't have to be tracking physically every single element. So there was a group in Texas that did that, and it was brute force, and it just took forever to simulate a resist. But if you just use probabilities, the amount of calculation time is dramatically reduced. You can actually do a lot more complicated stuff, and I'll show that. So here we have converting E-beam ionization to deep protected or protected sites after post-exposure bake simulation. And so we're looking at plots as a function of depth. This zeros the surface. And what I wanted to highlight here is that within the first 50 nanometers, there's a big change in the density of the chemistry that you're generating in a resist. This is assuming two things here. We have what if we have evaporation? The acid that is wiggling around here at the top surface, what if it just evaporates and goes out of the surface into vacuum? And so this would be the actual density of sites. And this is if it was not evaporating. And so, but the thing is that at the end, what you're seeing is that it's not a uniform chemistry across in the thickness of the resist. There's actually a gradient. And some of this stuff explains, like in HSQ, for example, people know that the really thin HSQ, you need a higher dose to expose it. As the thicker it gets, the dose gets lower. That's because of this. The probability of having an event, you know, it's different. So let me see here. Yeah, let me jump this because this is more. Yeah, I apologize. Yeah, this is just as a function of dose. So it's the highest dose. This is the medium dose for positive, negative resists. And but because of time, I'm already at 8 to 10. Here's an example of simulating the. Let me see if this works properly. Oh, I think it's going. Come on. Okay, here we go. So on the top is that the solubility or the chemical map. This is the topography of development, and as the dose increases, you see the evolution as how the solubility increases because you're changing this color to blue, which is soluble, and this is how it goes. And then for a negative resist, is the other way around. It's insoluble, and sorry, it's totally soluble, and then little it becomes more insoluble, and this is how it goes up. Yeah. So we can actually simulate the contrast curve if need be. If you know all the concepts. So this is just a summary, just to show. And interestingly enough, in the negative resist, this buildup of topography is a lot slower than here where you have the positive resist, and there's this catastrophic drop. And the reason is that in the positive resist, the regions that are soluble are originally isolated. Then at some point, you reach the percolation limit, and they join, and then large chunks of insoluble resist will come off. And so then you have, and so this is why positive resists have higher contrast than negative resists. You'll see it. You can look at any of these resists, and they always have higher contrast than negative resists. So this is now a 3D representation of what's going on. So here we have, as I said, this is just the energy loss locations, which is it's interesting but not very useful. Then you got the acid diffusion, and then you have the chemistry, the deprotection, and then you got the development. So this was for a positive resist, so you can see it's gone away. And this line-edge roughness can be compared actually with experiment. Let me see, this is just a frontal view of this maps again. And it's interesting. So here we're looking through the projection of a very thick film. But if you actually take a 2 nanometer slice to actually see what the localized population of things are happening, it's very interesting. It's just very, very minimal. You can barely see an image there. The statistics within a 2 nanometer slice is very, very low. But because this is a 3D thing going on in depth, eventually you will have, see, this is cool. After the acid, there's very little going on, but it's the accumulation of deprotection is what makes things join together. And so in that 2 nanometer slice, you can see there is a pathway for the developer to go through, and eventually, yeah, you'll get that. This is just the evolution of post-exposure bake, just to show how it goes in that 2 nanometer slice. All right, this is let's see if this works again. All right, hold on. I want to make sure I get this right. If not, we'll just. All right, doesn't matter. Let me jump. Okay, so yeah, this is one thing I want to highlight: the chemistry. So remember, the polymer on the surface, unexposed polymer, has a certain, bonds and dangling bonds and states and stuff like that. But the sidewalls are damaged polymer. And so the actual chemistry on the sidewall is different than the bulk chemistry. And so that's something to be considered, I assume, for like gratify and etch resistance and other things, that this is not your same polymer that you had before, because it's been partially deprotected or partially damaged, or in some cases, okay, did you hear that? All right, so this is just an evolution in time, how we're gonna develop, and you can see how it starts to see this little surface roughness in the top, and in time, it's gonna start going in, and this is that combination of ray tracing and cell removal, just to show you what's going on. And I'm doing this really narrow, unexposed lines on purpose. And what you see is, if it's narrow, you may have porous resist lines here. So it's not your standard polymer anymore. It's got porosity damaged all the way through, because secondary electrons at 100 keV can travel almost 100 nanometers laterally, left to right. Yeah. So depending on the thickness and so on. But yeah, it's about order of magnitude, let's say 80 nanometers or so. So if you have a really narrow thing like 45 nanometers, don't expect that to be the exact same chemistry as a regular polymer. Okay, so this is just jumping through different KVs, and you can see the chemistry and so on. I'm going to jump through that. But yeah, on the top, this is pMMA versus chemical amplified resist. The pMMA, so simulating the pMMA and the dissolution of pMMA, and then comparing that to the chemical amplified resist, you can see that because I need higher dose, I'll get better statistics, I get better line edge roughness, and better resolution than the chemical amplified resist. And these are actual. This is how many electrons I needed to simulate that particular dose. So again, yeah, the model seems very complicated, and it has all these formulas and lookup tables that you need to put things together for the Monte Carlo stuff. But you can actually get practical results even with that. I mean, this is not something that took a week to simulate. This is just I think an hour or so. I also want to bring this up. This dissolution model, where we're doing ray tracing and cell removal in together, and I'm using a 2 nanometer cell volume in order to simulate the resist. On the top is simulated surface roughness for these particular doses, and the bottom are AFM scans of this resist at these doses. And so you can see, yeah, I mean, it's not exact, but it's definitely following that trend where, yes, you are, for very low doses, you're going to see potholes at the beginning, and then afterwards it'll dissolve away. And on the right-hand side was, okay, let's see if we can do line edge roughness. So this is just a side view of a resist that was exposed, and the roughness that you would see with a top-down SEM, and here's what they look on the sidewall. Then down here this is the so the AFM trays simulated, and so the roughness that I got from a simulation versus the roughness of the SEM. So this is the SEM trace RMS. We got 5.7. The experimental was 3. So it's about the right order of magnitude. It's close. So this is pretty decent. I mean, it's not perfect, but I think from a point of view of understanding where line edge roughness can come, this could be used for that. And this is the final showing that. So simulated negative resist, and this is an SEM, and you can see that roughness that you see is very similar to what we simulated. Okay. Resist sensitivity versus resolution. Empirically, people know that HSQ, pMMA have the best resolution. Will also have the highest dose needed, and it turns out that it has to do with shot noise. The difference is that literature or textbooks will say you need a 10% uncertainty or your incident exposure to resolve a particular feature. But when I compare that, so here we have a minimum exposed feature size as a function of dose at 100 kV, and all of these are different resists that I've tested out, and I'm highlighting a few with the names. So this is stuff that I did at Bell Labs, and they were trying to get into this regime. They wanted on the order of, 20, 30 nanometers at 10 microcoulomb. That's where they wanted to be. And it turns out that no matter what we did, we weren't getting there. And it turns out that the reality is that the shot noise model they were using was wrong. Turns out that you can't get any better than 3% uncertainty. No resist that I've worked with, and I've got 30 years now working with resists, and I'd be happy if somebody surprises me that you can beat this limit. Nobody's been able to get beyond the 3% uncertainty. So yeah, even cold develop pMMA, even salty develop HSQ, yeah, you can't beat that limit. And the reason is that, as I said, typically people have been looking at this as a 2-dimensional problem, and in reality it's a 3-dimensional problem. As you're seeing all my maps, you have to consider the thickness, and you have to consider the statistics within the thickness of the resist. And just a very naive, simple way. Okay, so instead of just looking at 10 by 10, I gotta go 10 by 10 by the 10 in depth. And when you look at that, yeah, there you go, your 3% uncertainty. So it's very interesting to see that a very naive way of thinking of stuff matches what we're getting experimentally. So yeah, this is the shot noise limit for EV lithography at 100 kV. Cross section, whatever may change for other kV. It'll be interesting to see if somebody works on this at different kVs, and we can get some type of universal law on shot noise for different energies. So yeah. Okay, goal develop. This is where yeah, there's some request for this, and again, there's different things going on. Developer molecules diffuse. There could be some swelling. There's other effects that happen. You got mass transfer, especially if you have like a contact hole, little tunnel. You gotta have developer going in, and you gotta have all the stuff that got removed have to find their way back out, and so those things will come into play. There's issues with concentration of the developer, time surfactants, temperature range, and even the type of drying that you use. And so this is a typical thing I showed in the past where, yeah, going from room temperature, you get this particular awful step up, and then using a Peltier cold plate, so you can get to -4. Exact same, it was the same dose? Probably, yeah. Extremely nice. The line edge roughness is just so much better. And so we wanted to understand what's going on with cold development. Why does it work? And and we're just showing here that the dose needed 30 seconds room temperature versus -4 at 30 seconds went up significantly. This is if you develop longer, 6 minutes, then obviously it goes down. So you want to keep it short in terms of development time if you want to have the maximum contrast and stuff. ZEP the same. This is a contrast of ZEP, which is another positive resist as a function of temperature. And so going from room temperature, which is here, to like 0, you are basically going 60% increase in your contrast, and then you can double it if you go to -17. And that's just the -17 is no reason except for the fact that was as cold as I was able to get with the cold plate. That's it. It was just a limit on my hardware. But what's going on? And so you have to consider that the pMMA has a molecular weight distribution, and what you're doing is you're chopping it up like spaghetti, and you're creating new distributions. And so trying to understand what is that distribution or molecular weight distribution as a function of radiation chemistry, this is the guy to look at. This is his paper. This is who I got all the formulas from him, and I was able then to calculate what was the distribution of molecular weight as a function of dose for different doses. And so I started out with a single molecular weight, and then as I started exposing, so this is a low dose, so you have still a lot of unbroken chains, and there is a broad distribution of different types of molecular weights. And as you increase the dose, then this obviously is going to go down until at some point all of them are chopped up, and you have now this distribution of molecular weights. And so what happens is, okay, so yeah, so it turns out that the glass transition temperature of a polymer is a function of its molecular weight. So the chains that are highly chopped up have a lot lower transition temperature, meaning they're mobile. They're mobile at lower temperatures than a very, very long unbroken chain. You need a lot more temperature. You need a lot more heat to start moving the very, very long chain compared to a little guy that's just wiggling around. Think about it as degrees of freedom. And so that's what happens is that, when you're exposing resist, you'll have regions where it's directly under the beam, where you have a lot of scissioning going on. But because of the scattering, you'll have other regions where you have some pockets where the electrons stopped and start just chopping up there. But you have a transition of lot of dose, little dose, medium dose. And so you have different type of polymer molecular weight distributions as a function of position. And so when you lower the temperature of the developer, you're moving this down, and so you're freezing out. Basically, you consider this, you're freezing out the long molecular weight chains, and so then you have see, it's 1 over the molecular weight. This is the dissolution rate, and so the TG is also 1 over the molecular weight, and so this is what happens. You freeze them out. These are no longer moving, but these that have lower molecular weight, they're still mobile. And so these get developed out, and you literally are just then freezing out everybody else near here. These guys can still be developed, and you get the better resolution. So this was proven, and so this is just CDs, and this is done. In order to get these accurate measurements, we did after liftoff. I don't trust SEM measurements of resist alone, because you're degrading the resist as you're using the SEM for imaging. So we found a technique to get really good resolution on liftoff. But you can see here just the effect, how things just drop down for the same relative dose. And yeah, it's pretty dramatic, the improvement that you get. And so here's the thing that we learned. Typically, it's, oh yeah, chrome gold, and you get your nanowires. Well, it turns out it's not a continuous nanowire. The gold will ball up, and it does not wet properly chrome. And so you can't really use this for much, nanowires and stuff. So palladium has a very small grain size, and it wets chromium a lot better. And so this is palladium on chrome. And this was just sputtered. No fancy E-beam evaporation. This is just a little old sputtering tool in some little old lab in Argonne that I found. And so we were able then to do these measurements. You can see these 13 nanometer lines doing that. And so, yeah, because it was sputtered, we got some coating on the sidewalls of the resist, but the resolution is what I was looking for. And so, yeah, this it is. So, okay, this is in ZEP, and you can see the difference in resolution here. Here are the doses that we used for that. I'm gonna skip this. Does not work with chemical amplified resist. And the reason is that in the previous case, we're looking at a solvent which is diffusing and is removing a molecular weight. And here, it's a reaction going on. The developer is actually reacting also with the polymer. It's not a solvent removal. And so, yeah, 0 degrees in room temperature, and basically it's the same. This is a contrast curve, basically the same dose. So there was no effect in chemical amplified resist for cold developed. You can get too cold, and Ryan Cord did a fantastic job here. It's MIT, going really cold, so liquid nitrogen cold, and at some point you get too cold that you are just going cross-linking, and you don't get the clearance at all. So this is a contrast curve as a function of dose for different temperatures, and we know that at some point when you expose pMMA too much, it becomes negative. Right, and so let's suppose yeah, this blue is positive, and then if you keep on going, it starts to show up again, and so on. But at some point, it's just does not, when you're exposing. This is interesting. When you're exposing pMMA, both things are competing. Scissioning and cross-linking are happening at the same time. It's just that at low dose, the scissioning is dominant and the cross-linking is not as dominant. But as you increase the dose, the number of events of cross-linking start to become dominant. And that's why you have this change in tonality in the resist. And HSQ is the opposite. You heat it up, and now you get better resolution, and you get better contrast. And I've used this 50 degrees C. It's pretty nice. Yeah, and so this another work presents the 3 beams. So I'm gonna skip that. You can get too hot. So this is an organic resist, and you rinse it at 90 degrees C, thinking, oh, it'll get something better, and just looks like spaghetti. So yeah. Here's where trying to explain why this cold develop and hot develop improves your shot, your line edge roughness. If you explain it as a signal to noise type of problem. Think about the noise as just the random distribution of chemical events, right? Your 1 sigma, your standard deviation of how many events per unit volume are in the resist, and your signal is your incident dose, right? And so so that's when you're in the exposed region right underneath where the beam is, you'll have so many more chemical events. Your standard deviation or your distribution of chemistry is a lot less. So you have your line edge roughness is a lot less. So if you can get your developer to come into this region, you're into the region of large signal to noise, you have less line edge roughness. And so for a positive resist, you're freezing things out. For a negative resist, you're removing the partially cross-linked polymers from the HSQ, for example, the partially cross-linked HSQ. And so you get into the regions where everything is highly, highly, highly cross-linked, and you get better line edge roughness. Okay, so hydrogels. I know I'm not too bad. I'm a little bit over. Very quickly, hydrogels will respond to an external medium, and in this case, it could be heat. So here's the problem. Status quo was that you had to do this polymerization, and hydrogel, oh, well, then it has to be done in water. The high polymerization has to be done in water. And if you have to do it in water, you have to have a fluid cell, and because of that, the distance between your mask and the hydrogel is far away, and so you can't do really high resolution work. And so the best thing that people could do was in the micron range. And that's like, really? It turns out that we thought in looking at the mechanism, water has no role in the cross-linking of hydrogels. It's just the electron, and it comes in and reacts and it cross-links. And so let's treat it as just a regular negative resist, a poor man's resist. And in this particular case, NIPAM was the hydrogel, and the characteristic of that is that it swells when it's in cold water and it contracts when it's in hot water. And so we say, okay, well, then we're going to use the water, cold water, as our developer. And so we, this is the property I'm talking about. It contracts at high temperature and it swells at low temperature. This is the stuff that we want to do. And voila, it works. These are examples. So this is written at 30 kV. This is how it looks like after being in water at 10 degrees C. And then we put it in water at 40 degrees C. And this is the exact same location. And you can tell because, see this defect right here? The same defect right there. So we're not faking this or just saying, oh yeah, look at this, it looks better. No, this is the exact same thing at 2 different temperatures. And so after exposure and developing, we can go back and forth and we can see the expansion and contraction of the polymer. And that was pretty amazing that we accomplished this. And so we achieved like 70 nanometer resolution. And that was just the resolution of the Wraith 150 at the time. You see some of this wiggling. That is a polymer phenomena. It has to do with stress, and pretty cool. That was characterized by Vijay. He was at NIST, went to NIST, and he studied these things, and we got some really interesting results out of this. And so let me skip this guy. for now. So that's pretty cool. So we actually do fancy stuff. One fun application in simulating, and this is pretty much almost at the end. This is a 3D structure, and we're looking at HSQ, and we're trying to make some fins that were freestanding with an anchor. And again, trying to use the Monte Carlo code and then the chemistry code. And so this is the mapping. This is looking sideways at this fin. So the fin is sticking out this way a little bit. I didn't expose the entire stuff like this, but I had something sticking out. This is the contribution from the back scattered. This is inside the silicon. And this is frontal view. So we're looking into the fin. So you see the high density stuff there. And this is the mapping of the chemistry, and here's the develop. And if you look at that, it looks very close to this. So yeah, I think that there's a lot of fun stuff that can still be done and improved. And I think that hopefully you guys found this of interest. And thank you for your time.